Hello, everyone. Hi. Okay, so I'm trying to explain the problem that we saw in class once more. So let me bring out the slides that we used back then. So we were talking about trying to come up with a basic Bayesian inference method for looking at how many, let's see, it's this one, yes. Let's see how, we're trying to make inference for proportion. We're trying to make inference for the proportion that the percentage of all Vassar students stayed up at least one night last academic year to get schoolwork done. Okay? So what we did in class was we first we're going to try to come up with the prior as a whole class. So I'm going to explain that again. And also we took a random sample, supposedly random sample of 10 students in our class and assume that that's a representative sample of all Vassar students and use that as the data that we get. Okay, so remember for Bayesian inference, you start with the prior, represents your personal belief, and then you're going to collect data. And then once you collect the data, you're going to update your prior. So in this case, we're going to update the percentage, the belief of the percentage of the proportion, like the percentage of the Vassar students who stay up at least one night. All right, so what we did last time, let me bring back the slides here. I'm gonna write again of the particular prior that we came up with as a whole class. So if you remember back then we had 20 students. So let me write this over here. Okay, so we have 20 students, okay, 20 students. And we asked each person to vote as what is your belief, just 1 point. What is your guess of the proportion that the students stay up at least one night? So let me write it out again. So we got 0, 4, 0, 5, 6, and 6, 2, 0, 1, and 0 everywhere, okay? So this is the prior, okay? This is a belief before we see the data, and it's defined by the consensus, meaning that we asked everybody to vote, okay? So this is the prior. And the data that we get, I remember in class, let me write it down over here. The data that we get is we asked 10 students, and we saw one student saying that, I think it was Eli, and that he stayed up one night last academic year, at least once, to get work done. So this is the data, this is the prior. So remember for Bayesian inference, let me actually write it down over here. Suppose we're curious of this parameter, trying to make inference of the parameter. And we know that for Bayesian inference, posterior equals to the prior times the likelihood over this, okay? So posterior, here, this was the prior, this was the data. Sometimes we also call it likelihood. And here is the likelihood marginal. Okay. So let's see how to figure this out. So in class, I showed how you can use a pre-written R function to do it. But for this video, I actually want to slow down. I want to show you the R function is really just to facilitate the computation. If you are patient enough, you can actually do this particular Bayesian inference by hand, even though we usually don't do it, but I still want to show it how such an inference is done. So pretty much we're trying to use what we just write down over here. Okay, so let me bring a whiteboard over here, and then let's just do it all together. Okay. All right, so what we had. So we got, let me just write things over here. Values, and let's use theta tilde to represent that. And the prior probability. And to write it in the form that we know about is the probability of the theta tilde, okay? And then the likelihood or data will be y given theta, okay? So this is what we're gonna work with. Okay, so let me show you how to do this computation by hand, and I'm gonna try to build it up step by step. So remember, let's see, so the value that we have, 0, 0.1, 0.2, 0.3, 0.4, 5, 6, 7, 8, 9, 10.1. Okay, and what we had before, what we had is, for the prior that we came up with, so the 0 out of 20 chose 0, 5 out of 20, 6 out of 20, 6 out of 20, and then 2 out of 20, I think we got a 0, 4.5, and then 1, 4.6, and everything else from there is 0. So you see, if we try to list it here, you will see all of the values that you have for this particular proportion from 0 to 1.0. That's 11 options here. And we have 11 probabilities associated with each of the value, and they add up to 1. So now the problem is, what is the likelihood here? What is the data? So remember, what we had here is, let me write this one first. We have 10 persons that we asked for whether they put up one night. If you think about any probability, say 0.1, for example, over here, and then if I'm looking at, so for 0.1, it's 5 over 20, so that's 25%. 25% guess probability assigned to that particular value. So if you know this probability 5 over 20, and then if you know that you're looking at the value of 0.1, think about it. So the probability is 0.1, and we're gonna have y, in this case, is only 1 out of 10. So this will be, if you think about what is tilde over here. So y is the number of success that you're gonna get, meaning that, so we define success here as the number of people who actually say yes to that question. If you know what theta tilde is, it's gonna be a binomial distribution, so it's gonna be n choose y, and then your tilde raised to the power of y, and then 1 minus tilde, the failure probability raised to m minus y. Okay, so generically, for any, so now if I plug in, say, n is 1, n is 10, y is 1, so I'm gonna have this particular probability over here. Okay, so now if we're gonna try to fill out the last column over here, what we're gonna do. So if tilde is 0, what we have, okay, let me actually rewrite over here because I think it's too crowded. Let me just write, okay, so I was trying to write data, and we're gonna use this notation here. Okay, so now we know that for no matter which theta tilde you're looking at, it's gonna be a binomial data model over here. So you're gonna have n choose y, 0 to the power of y, 1 minus 0 to the power of n minus 1. So if we know all of the numbers that we have is 10 choose 1, 0 to the power of 1, and 1 to the power of 10. Power of 9 over here. Okay, so that's when tilde is 0. And for tilde is 1, then choose y, but tilde is 0.1, sorry. 1 minus 0.1 to n minus y. So that's going to give you 10 choose 1, 0.1 choose 1, raised to the power of 1, and 0.9 raised to the power of 9. Okay, and we can do that for all of this over here. And it's going to be the same form. Okay, so now let me bring back the memory of the Bayes inference method over here. I'm trying to, like I use this table, try to figure it out step by step, because in the end, what we're trying to compute is to use Bayes theorem, say here. We know that it's gonna be the posterior, gonna be the prior together with the data likelihood divided by the margin of the data, okay? And what we learned before, few slides earlier actually, we're using a notation, use the integral. But in this case, because what we see is discrete over here, because for the value of theta, there are 11 values of theta, and we, theta tilde over here, and we list all of them. So it's gonna be, let me use theta tilde over here, and then y, and then over here we have 11 choice over here, right? Okay, so what that means, so for any theta, let me keep writing this on the top, p theta would just be one of any of the values over here. And py given theta, we know that already, it's gonna be n choose y, because it's a binomial, and theta to the power of 1, and minus 1 minus theta to the power, let me write y over here, just to keep consistent. And then for each of the item here, it will be the same. And choose function and y, and choose y, theta tilde raised to the power of y, 1 minus theta tilde raised to n minus y. Okay, so obviously if you look at this, we can simplify a lot of things. So for example, because every term, so down here in the bottom, there are 11 terms, and each term has this n choose y. So if you try to do it by hand, we will be able to, I think, yeah, cancel out probably only these terms. So what we're gonna have is, so let me plug in the value of y and n over here. So it's 1 minus theta, 9, and then we're gonna have a bunch of different values. So let me just list like from the first one. So the first one is p equals to 0, and then 0 raised to 1, 1 minus 0 raised to the power of 9, 0 over here, okay? Plus p1, and then at 0.1, sorry, 0.1 raised to 1, and then 1 minus 0.1 raised to 9. Okay? And then until you get the last one. Yeah, 1 to 1, 1 minus 1 raised to 9. Okay, so obviously, in order to come up with the posterior probability for each of the theta tilde, you're gonna do all 0, 0.1, 0.2 until 1.0 for all of the different values here, and then you will be able to compute and then create like another column over here, say another column over here to record the posterior. Okay. And what the code, so let me actually bring this back for the code here. The R code that we used in class, and I actually shared with you as well, is trying to, let me bring this up, give me a second, our studio, okay, let me share screen. Okay. Right, so this is the code that we used actually. So I updated the code a little bit and I posted the new version on Moodle so you can have access to it as well. And you can read, so first of all, in our studio, you're usually gonna write your comments in this way. And then so here, let me just explain it again. Prior values that we have 11 different values, 0.1 until 1. So we have, yeah, I created a vector to record all of them. And I also created a vector of length 11 as well to record the probability associated with each of the values that we came up with. Okay, so that's why you have 0, 5 out of 20, 6 out of 20, etc., over here. So this is the prior. Okay, and here I wrote down the data as well. We have n equals to 10, and 1 says yes. Okay, so this is pretty much just to create a vector later. Because I tried to compute, remember the particular column that we had earlier, how to get the likelihood for the data. Okay, so then I wrote here a loop. Okay, it's a for loop. And I'm doing it for 11 different values. So pretty much if you're gonna round this length, prior values is gonna be 11. So I'm trying to do it for each of the 11 values over here. So first of all, I compute the binomial probability given value of P. So you see that, D binorm. Binorm stands for binomial, short for binomial. And D is trying to compute the density, okay? So for this in R, this is the pre-written function in R. And then what you do is you fit in the Y value, in our case is 1, the N value, which is 10, and the P, which is the success probability, going to be the ith value of the prior values factor. Okay? And then that's only for getting the likelihood, okay? Because it's a binomial binomial likelihood, and I fit in each of the prior values from 0 to 1. And then I'm going to compute the joint probability. So remember, in the formula that we saw before earlier, you're going to have P theta tilde times P y given theta tilde. Okay, so binomial prop is this y given theta tilde, that's the likelihood, and this prior prop over here is probability P theta tilde. Okay, so let me say this again: the likelihood. This is the data. Oh, sorry, give me a second. This is the data likelihood, and this is the prior. They're both in probabilities, and we multiply them together in order to get the contribution of this particular prior to the joint probability. Okay, so after you run this for loop, you're doing the multiplications for each of the 11 pairs. And then in the end, remember for the Bayes theorem, down there we have Py, that's the marginal probability of the data. So we're just simply summing up all of the joint probability that we computed before. All right, so let me run this. So, and then we can see the results. So I explain all of here, and then we're gonna compute until this point. Okay. Right. So you see that once you run anything on the global environment, on the right, top right, you will see all of the values that you created. Sometimes are scalars over here. Sometimes, sometimes they are the vectors, as long as like depends on what type of value or type of data that you specified. Okay, so we have now the probability of y, and then the posterior probability we know that's going to be the ratio. It's going to be the joint probability for one particular value over the total. Okay, so if you run that, that's going to give you the posterior. Okay, and then I created one more. I just combine all of those values together into one data matrix. So you see that. So earlier when I was doing the writing on my iPad, I'm trying to show you the table that I was trying to come up with. Remember? So I had the first column to be all of the prior values. I have 0, 0.1 to 1.0, and the prior probability here is represented in the decimal points, okay, instead of the ratio. So you see that is 0 for 0, 25% for 0.1, etc. And the posterior probability is what we just computed using our R function, okay? So in class, I show you this really quick, and I was trying to say that this kind of representation is not that easy to tell how the belief for each of the prior values changes after you see the data. So instead, we like to plot them. In this case, actually, in particular, updated the code for the plotting here. So if you look at here, so all of the plots going to show up on the right bottom on the interface. And this is really just a rough representation over here. You can do much better. But over here, I wanted to show you that, okay, so if I start, so you can see, so I plot, actually, let me plot it one more time, just step by step. Okay, so you see here, this is the prior, okay? And the prior probability, so on the x-axis is the values. It's 11 of them. On the y-axis is the probability that we came up with as the prior, okay? And then let me show you, I put an add line over here showing that I actually like the data is at this point, okay? And the data I just wrote down, if you see over here, is 0.1 because we have y equals to 1 and n equals to 10, okay? And now, after using the R function, I actually compute all of the posterior probability for each of the prior, for each of the values over here. So you will see that I plot it one more time. And I'm using this cross symbol for each of the point, and I also use this blue color to show the difference. Okay? And then in the end, we use something called legend in R. It's usually depends. It can be on the upper right-hand side, and then it's going to be a box, and then you're going to show the reader of the plot what are each of the dots means and what the color coded, etc., etc. So here, I think the story is the data at this point 1 definitely drags our inference, right? So because before we see any data, we have this red line, okay? This is our prior. And then the data is telling us, okay, it's probably going to be 10% because the particular sample that we got, we have 10% of people actually say yes. So if we combine this information with the prior, you see that the blue with the cross symbol is what our posterior probabilities are. Okay? And you see that definitely comparing to the prior is shifted to the left and being dragged by the data. Okay, so this will be definitely like comparing to what I had in the class, in the lecture. This is definitely a better representation of showing you how Bayesian inference is done. So first of all, I explain all of the code over here, and then I run it. And second of all, in this particular plot over here, you will see how the data, this particular green line, and the prior, the red one, together make a contribution to the posterior, which is the blue one. Okay. All right. I think, yes, let me share over here. Yes, I think that's all I want to talk about for this particular problem. I want to slow down the process to show you actually for this particular problem, you can do it by hand. And then that's actually an exercise of Bayes' theorem and then how Bayesian inference is done. And then I also wanted to slow down for explaining the R code, because the R code is really just facilitating the computation. It's not something too fancy. But I understand not everybody has experience with R. So I also want to get this chance to demonstrate how things can be done. And yeah, I hope this helps you understand part of what we talked about in class. See you.